in your own house, then now you can sell and get some form of income from, yeah. So basically, it's someone who has, yeah, a little garden, yes, yeah. And yeah, about the political appetite, yeah. Uh, I don't think, yeah, right now, yeah, I don't think it's very feasible. I did actually try and look into that sort of situation, and it's sad that the farmers do actually see that they do need some form of intervention, but then, yeah, our politicians have promised a lot of times that they would come through for us in a lot of areas, and yeah, it's sad that the small-scale farmers are abandoned, and as much as they could play a key role in coming up with food security and improving a lot of things in communities, the policies have abandoned them. So, yeah.
Thank you. Thank you, Tinashe, for a great presentation. I'm a guy from a rural area.
Okay.
Very much interested in seeing, it being implemented. But as a person who got interest in the information security management, now, jokingly yesterday with my supervisor, over dinner, we were chatting, say, with these new technologies that we are proposing, but we need also to be mindful that there might be problems. Now, if we're saying, for example, the Internet of Things and other possible technologies that we introduce for small farmers, and then that could create problems whereby I hack into your system that you've got a tracker in your, I think yesterday it was present, I think during the round table where it said that I think in Kenya or Uganda, where there was a sensor for cow to check their temperature and what. So if I were to be able to hack into your cattle and then steal information or poison your cattle, so I can be able, the only one that is in the area, farming and then selling. So I'm saying maybe for future studies as well. Okay. Thanks.
A comment from you? Thank you for the question.
Thank you for the question. So, as much as, we are all in IT, we know we need to also have a feasible result to our research. So I actually have done my master's, and this was just one of the case study areas. So we do have an IoT solution that we've actually made. That's why I was very confident when I was mentioning soil moisture sensors and soil pH sensors. And so far, we've used it for the past 2 years. And I'm not really sure what hacking needs to be done there, because it's just ultraviolet light, pH soil, and soil moisture and stuff like that. If you were to hack into something like that to improve your own agriculture, then I guess we're winning. So, yeah. But thank you for the suggestion. Sure.
Thank you. More questions?
Good afternoon. Have you heard or had to do with Self-Help Africa?
Pardon?
Have you had anything to do with Self-Help Africa?
With Self?
It's an organization. It's non-profitable.
Oh, no.
It works throughout Africa.
Oh, okay.
And they do incredible work. The last I saw from their data, they have $30 million per year budget, and they go in all these countries, and they're doing a terrific amount of work for people under resource poor conditions. And we are sort of cooperating with them, not on the financial side. We're getting funding mainly from abroad. But I just wondered, because that may be worth while following that up.
Okay, thank you.
I think that's a very good point,
Yes.
because we might be looking to the government for many solutions, but there are also other channels
Yes,
for getting assistance to the people who really need it. Thank you so much, Jan.
Thank you. Thank you.
More questions? Okay, wonderful. So I think, Tinashe, the audience is satisfied. Thank you so much.
Thank you.
And now I'll introduce the second presenter. Our second presenter is Jan van Wyk. He has been a researcher from 1968, and I think that's like about 55 years of experience. And when I asked for his introduction, he just asked me to mention one thing that he's not been able to really solve. He's a parasitologist, and there's a particular worm, wire worm, that he's not been able to really address. Jan, we're looking forward to hearing from you. Welcome. His presentation is on GSOC tools, geospatial engineering and technology supported climate sensitive, Sericea Lespedeza, fodder production sustainability analysis modeling in the southeastern United States. Thank you so much. He's from the University of Pretoria, UP.
Thank you very much, brother. I'm glad also for the chance of coming here. I can't say I haven't managed to do anything against that worm since 1968, but the big thing is it is still winning. And the main problem is anthelmintic resistance to all the drugs that are available. There are 7 different unrelated anthelmintic groups. And really recently we found a strain of Haemonchus that is resistant to every one of those groups. And it takes about, in that case, resistant to everyone. And it takes, the 3 newest ones did not work at all. And it costs, the estimate in the literature is it costs $204 million American dollars to develop one new anthelmintic. So we're in big trouble as far as that is concerned. So this I'm giving a talk in, it's from groups. We're forming groups from the United States and Britain and other places. We've done a bit of work in Botswana and Malawi as well and that sort of thing. That's the sort of thing that we're busy with. And then, so I just want to say one thing, that I have, a lot of this is mathematical modeling, and I am as dumb as a doornail as it comes to modeling, so I won't be able to ask your questions on mathematical modeling. Okay, so the rationale of sorry, let me click. Which one? Yeah. The rationale of this is that there's a very good crop. It's called Lespedeza cuneata, and it has anti-helminthic effects. It's very good for farmers. It has worked very well under resource poor conditions, and it's one of the things that we are concentrating on, this whole thing of getting things to the resource poor farmer, mainly, because then later we can build on that for the other, for the commercial farmers. Then the parasites are across the board. I mean, just this one I mentioned, but that's nematodes, trematodes, and cestodes. So it's practically all the worms. They're all giving a lot of trouble. And then the big problems with it, one is the resistance, the other is the cost of the anthelmintic drugs, the fact that environmental concerns, is that, oh, I got the wrong one. Where did I go now? Sorry. So this is which is the point to that one? Okay, right, thank you. So now, the point is that with these things, it means that they're also looking at the drug residues in the food, the drugs landing up on the soil because they come out with the feces of the animals, and it's making research more urgent in this field than before, that and the resistance as such. And then unfortunately, this crop is not easy to grow, and but we are making use, getting the modern technology is making things so much easier. It makes it so much, in other words, there's so much we can do with it. And we must look at the potential of what we're doing. In other words, it's a matter of not only doing research, but having it sustainable so that it carries on and people can work with it. You see there that and then the other thing is that with small ruminants, the worms are the worst, and they're making quite a lot of problems in the United States. They're taking over from cattle for many reasons. As you know, in the resource poor farmers, sheep and goats are also used more often for actual survival than the cattle. As cattle are, you know, but anyway. So that's a very important thing. And then the thing is that with you see that the modern with making use of this technology, you can see now to be able to follow Lespedeza, it used to be known as a weed because it tended to spread wherever it went. But they've developed a lot of new research. With new research, they've developed new forms of it. You must excuse me, when I had COVID twice, so suddenly when I think of a new word, then sometimes it's gone. So that gives me a bit of a problem. Okay, so the first thing we looked at is this matter of precision agriculture decision support. The second thing is, that's the most important as far as I'm concerned, is to make use of the technology we have, and that what the meaning then in this case, automated training in information for farmers and leading them, and then training for them under those conditions as well. The scope, the new varieties of Lespedeza are not, they don't spread, and they can be, it can be used very, very well. And so the thing is that we make use of site-specific fodder management to be able to follow what's happening and find ways of improving the production of the thing. And so this Lespedeza is it grows well. It's a homogeneous crop. In other words, it's the only heterogeneity where it grows usually is weeds. So, and we make use of remote sensing from like a Landsat approach to be able to follow it. And where's the scope? Yeah. What we're doing is to make use of drones and that. So it can be, it's very, very nutritious. They actually speak about the fact that you can use it as an anthelmintic and to treat cattle and that, and sheep and goats. And treat them because then the worms are affected as well, both sheep and cattle and goats. And so it can prevent the things to a very large extent. Then the agronomic advantages are it grows in a wide range of soil types, including acidic, infertile sites. It's a legume, doesn't need nitrogen fertilization, deep-rooted, reduces need for phosphorus fertilization, it's drought tolerant, and it's very insensitive to insect damage and disease problems. And then it has a tendency to shed its leaves, in which case it then helps to improve the soil fertility and soil structure, and it has reduced soil erosion. The goal of the study was to develop this site-specific type of technology, as I said just now, and then to develop a protocol for field data sample collection, develop geospatial approaches to obtain the production and spatial variables to see what can affect the growth of the thing. And then develop models, algorithms, and that using statistics and artificial neural networks to find out how one can manage this crop the best. And why is that not? The study area is 3 states in the United States. That's where we're doing most of the work, but there's a lot other work being done in Britain and South Africa as well. It's funding from the states, but it's being done there. Okay, then for field sample, we just used a rope, put it down, and then we'd cut the Lespedeza there to about a couple of inches above the ground, and then weighed and analyzed, because the content of the Lespedeza, I won't go into that, but the contents are very important for the effects that the thing has. So the sample laboratory analysis, you can just see there's a lot of work that's done there. And the weight and average height as well to see for production of the crop. The data collection is GPS using field, and then non-GPS site addresses were geocoded. Both were appended in ArcGIS GIS to create all 20 sites and other sampling spatial locations. The then Lespedeza growing field polygons were digitized, and the land site and data were collected with a close proximity when it was close to analysis. And in a few sites, drones were used, unmanned aerial vehicles. And then, of course, we looked at soil precipitation, temperature rasters, things like that, that were very important, that are very important. Sorry, I'm going the wrong way. Is this the one? Okay. Normalized difference in vegetation index, soil adjusted vegetation index, just some of the things we're doing to have a look to see how this is being collected. Then the data downloaded as a point-shaped file, and that, sorry, am I going the right way? Okay. Here you can see annual average temperatures, just the sort of information that was collected. The average temperature maximum spatial distribution raster, and the annual average precipitation is collected in those 3 states in the US. And on that we built the data. You can see the type of thing. It's not important. Land cover, to be able to differentiate. First of all, register the amount of land cover in where the Lespedeza is grown and around it, to see what the conditions are. The slope, because it's not very sensitive to it, but that is just to test the range of what it can do. Soil texture, soil bulk density, it doesn't matter, it's the same sort of thing. And then as that the thing grows under all those conditions. Then this is just showed us the type of photos we get from it. Not we, the Americans are doing this, but this is what we're basing it on. And it means we can go on here and base our work on this sophisticated work being done over there. And you see an example of one of the rasters, just a plot of the plot, and this just to give an indication of what's being done. Sorry, I'm going the wrong way. Again, here you see land cover, slope, all those different things, and sorry, am I going the wrong way? Something wrong. Sorry. It's not going, it's not working. It's just going on and on at the same place every time.
So you're on 13. Let's go to 14. Are you able to move
Sorry.
to the 14th slide? Now that's 14. Go to the 15th. Yeah, now you're moving forward. Go to 16th. Try with the clicker. Try and see.
Yeah. But this is just also to show the type of models that are being developed. No, this is forward now, going forward. Yeah, okay. I don't want to discuss these things, just to show you, give you an indication of the type of research that's being done there, the modeling procedure, statistical multivariate analysis and artificial neural networks, ANN, all techniques that these people use, not me, I wish I could. And then this is the radial basis, again some of the modeling, and the prediction model result. In other words, what we want to do is to predict what is going to happen, to what extent one has to attend to the product, the lespedeza, when it needs to be reaped and that sort of thing, and in other words, how much food that you're going to have available from it. And then so that here's this mean line fit plots. Again, each one has a specific reason and a meaning for it. It's not important here. I just thought to show you, because this was actually written by Professor Sudhanshu Panda from India. He's working in the States for many years. And so I'm just showing he put this together, and he thought it was good for people just to have a look at that. And then the biomass estimation model, that's again, as I said just now, that the prediction model is more than 80% average prediction accuracy, and the data set is for testing validity, and for data set is 80. So there's a prediction and to get that done. So more modeling. The soil pH is not used because this is the product, the crop is very, it's not affected much by pH unless it goes really, very, very low. And then again, you'll see all these. Am I going the right way? Here you get an idea of the suitability map for the state of Georgia. So in other words, when we put all those things together, those are the places. Also, this professor, he has presented at one of the previous IST conferences. He actually modeled the whole of Eswatini for the topography of that, to see also and to be able to get this sort of thing for. So that's the level at we are. They are cooperating so closely here, and with the type of work I've been doing, resistance and trying to find new ways of getting it done. And then the production, the farms that were used in that thing in the States, the state there. And then this has gone faster than I thought it would, but anyway, it's the summary and conclusion. Field data collection and laboratory analysis process were developed. The model was developed for predicting biomass production amount after data mining, and close to 55% correlation coefficient values obtained. Radial basis function network provided more than 80% average prediction accuracies. We are now using multi-year data along with all possible plot-based sample location information from those states. So we're expecting a robust algorithm to predict SL biomass yield over this. So we are applying that. The person with whom we are cooperating in the UK he is the one who's had got the funding for the work we did in Botswana and Malawi. And I've done quite a lot of work in South Africa, not specifically on Lespedeza, except to find out where it can grow and that. But I've done a lot of work in developing communities, like for KwaZulu-Natal. And we developed one system that's very useful to look at what's the time like?
You have a minute.
Just for instance, to see the effect of the worm, we developed a system they called FAMACHA, that where you look at the color of the mucous membrane, the conjunctiva of sheep and goats, and it shows you what the effect of the worm on the animal is, because of that it's such an avid blood sucker. And that is, we developed it here. It's now has been used or tested in 45 different countries. So it's the sort of thing we're looking at trying to look at the whole picture, but then to get these people who are clever, like in the States and them, not me, to see the complicated stuff as well. So that's what I wanted to show you. It's the whole picture that we're working on, and to me the most important thing, and that's what's going bad now, is the sustainability of the research being done today in any of these fields is very, very poor. It's not being used later after that. Thank you very much.
Thank you, Professor Young. Very impressive results, and engineering of Lespedeza to help with fodder production. Thank you, sir.
Thank
Questions from the room? We can take questions, and I have 2 mics. Maybe I'll start off with one question. Oh, I've seen a hand up. So, Professor, maybe you can explain how, what your plans are for using this research within Africa, within South Africa. What are you foreseeing as the next steps, even as you see what has happened in the US?
I've been working since, because I'm a fossil, I've been working since 1997 without a salary. I'm completely dependent on external funding. And what we have developed so far, as far as the practical significance of this work, is such that now very recently we got a project that's worth about 12.5 million rand, together with from the United States, and we're working on all these things. And one of the most important things is an idea I have, whereby you see the problem with the developing farmers, the resource poor farmers. There's almost nobody at ground level to help them. The system of FAMACHA that looks so practical is not so practical, even though we developed ourselves, as I said, it takes too much labor. So now there are ways, cell phones, I read about, I don't know, maybe 2 decades ago, maybe, say 10 years ago, I read that in Africa, south of the Sahara, 80% of the people have access to cell phones or possess them themselves. 80%. We're not using that. So we're building all of our research on that type of thing to see, like now the Self-Help Africa, that's why I mentioned them. They take little groups of farmers in different villages. We were working, as I say, that wasn't my, I worked together with the people in the things, but working in, I think, probably about 40 different communities in Malawi and Botswana. And then to make use of the idea is, and in Brazil, they've developed a method now, we've been thinking about it for a while. They've developed a method whereby they can photograph the mucous membrane of the sheep or a goat, send it to a computer, and the computer can characterize it. FAMACHA has 5 different colors. It's red, pink, white, and white. So red is perfect, and white is, of course, almost dead. So the computer can do that now. So that can show you also the type of potential there is. Just to be able to use that, get the farmer to send in a few photos, and then have a look. The problem is that 80% of the worms are carried by 20% of the sheep. So you can't, unfortunately, you can't just take an aliquot of sheep or goats and then look at those and think you're going to manage without, every now and again, going a lot of labor to look at them all. But we're developing, and my idea, we're developing that at the moment, but I don't say it'll be there within any at all. Maybe it doesn't work because I don't have a lot of knowledge of that. So that's the point. That's the type of thing we're trying to do.
Thank you. Question?
Thank you so much, Prof, for such a presentation. It's just interesting to see how technology meets culture and mathematics, and it's just interesting to listen to the talk.
Could I just interrupt you and say my mathematics teacher said to me completely, every now and again he said, "Drama of time says, Van Wyk, why are you so stupid, man, you monkey?" So I'm still a monkey with mathematics. Okay, sorry.
But my question, Prof, is around the plant that you're talking about. Just a matter of interest. What is Lespedeza? What is it all about? If I can get one thing out of the presentation, what is it used for? Is it for food? Just out of interest, what is the Lespedeza all about?
It originated in China, and it was imported and it is used there as animal fodder. Because it's very useful as fodder. And now what we're looking at as well, it's difficult to get it started. I can't think of the right word now, to get it started. So we used, they're making use of drones, the unmanned, what they call vehicles. Yeah, making use of those as well, to see to judge the growth of it. It can take long to develop, and that's what we're looking at to get that going. And to get it then, say, to farmers, the problem with communities is that it's communal ground. And it has been tested to an extent there. It works very well with sheep and cattle, and they actually have some research done there where there are some Lespedeza and just ordinary pasture next door, and the animals prefer the Lespedeza. So in that way, it's a very, very useful, and it has all the qualities that I tried to bring in here. I didn't emphasize them enough, but that's the point.
Thank you. Another question?
Okay, now thank you, Prof, for a very nice presentation. I just want to find out how can this project be scaled down to local areas or local regions here in Africa, where we have sparse and what is it? Kind of sparse weather stations. Sparse, like a lack of weather stations here in Africa.
Oh, lack of weather stations.
Yes. So how can the use of free satellite images assist in that regard?
That's what the geospatial
touching on something that's very dear to me. The person in the UK with whom we're working, he is a mathematical modeler amongst others. He's a veterinarian but also a mathematical modeler. And he, in the whole of Africa, if you look, he's cooperating with the university in the UK for most of Africa. I don't say the whole, and it's not everywhere so accurate. But for every patch of 10 by 10 kilometers on the continent, as I say, just probably not so hard in place, some places not. But anyway, largely it helps a lot. It gives you the rainfall you've had there for the period of time, and it gives it temperature. And that's what causes the worm to develop. It doesn't. Why does it occur in the Kalahari and places like that? All these places, because it can last in the feces and that sort of thing, and in the animal for a long period of time. And when it rains, perfect. Now this person in the UK is now, but he has built models on that, so that we can then be able to tell the community. And then what South Africa is doing, they're taking, say, 2 or 3 farmers, they're getting them to have a look at their animals using our FAMOCHA method and condition scoring. You know, I don't know if you do that, no, that's something, condition scoring and weighing and stuff like that. And then having a look, and according to that, building models to be able to judge when you need to tell the farmer. Like for instance, here, in this region that the worm does not reproduce in winter. So you can stop doing that, the labor-intensive famacha for the whole winter. But how do I tell the farmer when to start in spring? I can't. And then, but there's so many things I can use. Like for instance, there's a huge difference in the susceptibility of lambs, pregnant or non-pregnant ewes and lactating ewes. Like in the trial we did, it was only 17% of dry ewes that were not pregnant, non-pregnant ewes, needed to be treated under perfect conditions for the worm, irrigated pasture, 17%. It was something like 22% for heavily pregnant animals, but 56% of the lactating ewes had to be treated. So it shows you one can use that as well, and that's what we're trying to build into this whole system. To say that when you at the beginning, at the end of the winter, or at any time, if you just tell the computer that when you're putting your ewes to the rams, like for commercial farmer, I know in resource poor that doesn't work, okay, but a commercial farmer can do that. Just say when he puts the rams to the ewes, and then the computer can tell that farmer, okay, looking at modeling that is being developed, is not there yet. But there is some like that, but not exactly what we want. But look at the model, and then say to the farmer you can wait until then, because we can take with artificial intelligence. Artificial intelligence, we've just done some work now, where we do activity monitoring using transponders to measure the activity, and also for worms like that, we were able with artificial intelligence, but there we had about 100 sheep with senders on them, transponders on, and we were getting 30 digits of data every minute for 24 hours and 365 and a quarter day per year. But with that, with about 18 months or so, for 2 farms who did the work, it was possible for the computer to estimate when an animal was changing from famacha, this system of ours, from 1 to 2. Now 1 is a hematocrit of 27% or higher, 2 is 22 to 27%. But the computer was able to pick up the difference in movement with 85% accuracy. So now I can go to the farmer and say, okay, you can look at more or less this time, but now when you do, you have to do all your most susceptible classes of animals. Look at all of them, put that back to the computer, using cell phone for photos and also the other. It's not there yet, but it's working already. It's a matter of making it work on a large scale.
Thank you so much. Any more questions? I think the room is satisfied. Thank you, Professor Jan. Thank you very much for your presentation.
I say thank you. Oh, I almost took your computer. Yeah.
Now, we transition to our next presenter.
I almost took your computer now. It looks just like mine.
Just to mention that, unfortunately, Hussein Serif will not be joining us because of the situation in Sudan, and our thoughts and prayers are with him. And we will be moving to our last presenter, Isaac Mwakabira. Isaac, welcome. Isaac is a staff associate and systems engineer in the Department of Computing at the University of Malawi.
Which one is this? This one.
He is currently pursuing a master's in informatics at the same University of Malawi, and his specialization is in monitoring in mathematics and statistics. He's going to be presenting to us a paper titled Design Gaps in Configurable Systems, Adaptability of DHIS2 to Other Domains. Welcome, Isaac.
Thank you. So as per the introduction, my name is Isaac, and those are the co-authors, Lawrence, Tuonge, Yankani, and Augustine from the same university. So I'm here to present on design gaps in configurable systems, the adaptability of DHIS2 to other domains. So this is just part of this work is part of what I was doing as Master of Informatics thesis. So the presentation outline, I'll start with my problem area, research objectives, then talk about the research approach and methodology, then talk about the major outcomes or preliminary results that have been found, and conclusions, and lastly, there's a slide for references. So, configurable systems and the resource area, low resource context. So the value of configurable systems in low resource context cannot be underestimated, especially when I understand all of us have done projects. So there are quick delivery timelines, and also there are financial constraints that they have to be met. Also, especially when you're working within such low resource areas, you do not have the human capital or human resource to carry out the software development exercises from scratch. So you would want to start from already something that is already working, especially from well-to-do contexts. So configurable systems have a primary domain of use. In this case, they can again be adapted to secondary domains. So they have a primary domain, but they can be adapted to work within other domains, which in this case I call secondary domains, without need for any programming. So why is that possible? It's because within themselves they are what are called configuration objects or metadata objects with generic properties, allowing them to be adaptable to not only the primary domain but also other domain use cases. So this presentation we're focusing on DHIS2. It has its roots here in South Africa, University of Western Cape, I think. The idea born in 1994, together with the University of Oslo. So currently the work has been continued since then within the University of Oslo. And as a system, it has two general data models, the aggregate and tracker. So mostly this work dwells on the tracker module. So in Malawi, it has mainly been implemented in health, which in this case is the primary domain. It stands for, so DHIS2 stands for District Health Information System. And recently, there have been some work in agriculture called NAMIS, for National Agriculture Management Information System. So reappropriating that system from health now to a secondary domain, which in this case is agriculture. So we've had some lessons or experiences from that, and from that work they've been reviewed several inherent design limitations in health-related and health-unrelated cases to do with usability and the relevance of the platform in solving requirements of the local context and domain. Also, the platform's flexibility in addressing requirements from the local domain. So why am I emphasizing on the local domain? It's because it's designed somewhere in the Western world, but used in the developing world. So you see that relevance issues come up, and also flexibility in addressing such local requirements also come up. Let me talk something more about usability. So we have usability could be in form of it's configurable. So you're configuring certain workflows that workers, or in this case, or end users, when they are using the application, would find certain challenges as they carry out their work, their daily work. So you have complex workflows, naming conventions that are not applicable in the secondary domain, but applicable in the primary domain. Also relevance, I talked about that, and flexibility. So in general, the platform lacks sufficient variability in the configuration objects or design elements. So these are objects or elements that are used to design UI, the UI that is used to used by end users to carry out their work. So as such, it fails to support multiple domain design needs. So therefore, the platform exhibits such configuration gaps in regard to its adaptability to other domains like agriculture in this case. Also, some work has been done in education. The same things are also reviewed, so including health. These are what we call specialized use cases, transactional level cases. So the research objective was to propose some design changes to both the configuration objects and the resulting user end tools or data collection tools. The goal is eventually to enhance them so that they become usable and easy to use by end users. So through this work, we've come up with a few features that we think can enhance usability and enhance or add more configuration objects that helps its adaptability to other domains like agriculture and education. So the research approach, we first conducted some interviews with a total of 31 frontline workers. Some they've not gone through formal education, they've just done some training and off they went to do some work. So I would call these agriculture extension development officers, and others were technical people who are involved in the design of different custom applications on top of the platform. So we selected these from 3 administrative districts of Mzimba, Nchisi, and Mchinji in the first months of 2022. Then we also analyzed inbuilt applications. So within the platform itself, there are inbuilt applications that can be used to configure different things. So we analyzed those for what things can we improve here and there. So we evaluated that, and the reason was to establish some inconsistent design flaws, their utility, and efficiency afforded from within its features. So following that, we developed a couple of applications. Here I'm only showing 2. One, it's an enhanced version of what is currently used within the community. It's custom Android settings app, so it customizes the Android application. So you have a web app that customizes the interface for data collection that is mostly used by end users. The second one is program variable and section application, so that also configures certain things within that. So the design process involved building and making enhancements on both fronts, the configuration part and also end user part. So that we understand, so that we come up with something that can be used efficiently within the domain or different domains. We used that participatory design methods, mainly prototyping. So we could prototype, then go and test with users. So major outcomes, we have new design alternatives other than what is provided within the platform. These increased configuration space, so we have more configuration objects and metadata objects within that to support adaptability to other domains. Also, increased variability of the individual configuration objects to support such requirements. Like in this case, we're saying toggling of stage action settings, where some naming conventions are not applicable in the secondary domain, which is in this case is agriculture, but they are applicable in health. So you want to hide certain things in the domain in which they are not applicable. And also, in the long run, there's that improved. We have an improved degree of adaptability to other domains. It could also be within the healthy domains, especially at transactional level use cases. In conclusion, we think the more granular configuration objects or configuration rules become, the more insufficient platform configuration elements can also become. As such, we need a flexible configuration layer that is needed to free the platform, in that it can be adaptable in any other domain other than its primary domain. Also, enhancing DHIS2 configuration layer with more variant configuration elements we think can free the platform from its initial healthy centric assumptions, and thus will prevent the platform from being specific to only one and preventing it to be adapted to other domains. So also additional various configuration elements in the DHIS2 platform would enable implementation level designers to explore, also provide and meet a set of usability design configuration needs and goals in any individual use cases. So reaching that far, I rest my case and I invite questions and comments.
Thank you, Isaac. Let's give him a hand. So we can take questions. Yes, thank you.
Thank you. Mamadou Bilem. I have just two small questions for you.
Yes.
My first question, can you give us an example of a primary domain and an example of a secondary domain? Second question, I have understood that you have adapted
DHIS2.
Okay, in order to be usable in other domain. Okay, that is the case.
Yes.
Okay, but why you do not start from scratch?
Okay, so so there are two questions. One is give examples of a primary domain and a secondary domain, and the other one, why don't we start from scratch? So I'll start with the first one, with the second one. So I hope I had a one slide on that. So low resource contexts are mostly, they mostly don't have enough human resource to start everything from scratch. So you would want to start from somewhere. You would want to use some solution that has worked somewhere and just customize it here and there, or adapt it, use it as it is to solve the problems that you have at home. So in our case, we wouldn't start from scratch because we also fall within that category. So we are a low resource context, and such we can't. So coupling with delivery timelines, you can't deliver something on time with the few resources that we have in that regard. So the first question was about an example of one for primary domain and the secondary domain. So DHIS2 primarily is meant for health. That's why in the acronym it's district health. So it's primarily for health, but it's now been reappropriated to some other domains. So recently there have been some work in education, in agriculture. So like in Malawi we've had one which I've presented called NAMIS in agriculture. I also understand in Mozambique also they've done some work on agriculture. In education, Mozambique also has done some work there. I think also Ghana or Uganda or something. In Guinea, I think, education. So primarily DHIS2 is made for health, but we're using the same platform to solve problems in education, problems in agriculture, and also there are certain specialized problems within health that the platform may not solve. So I was exploring in that area. Yes.
Okay, thank you. More questions? Anyone on user interface design?
She wants you to kill me.
I think for me, I just looked at the paper and I just want to ask a question, especially on the analysis. I didn't see much in terms of, you said there were 31
Yes.
respondents that you worked with,
Yes.
but I didn't see any particular statistics on their feedback on
Okay.
the design part.
Mm.
I don't know if you want to comment about that. Is it still work in progress? And would you appropriate some of that input coming from this test case to see whether it can be an improvement or not?
Okay, so we've done some similar work on the same. So on usability, we were looking at the time aspect and usability using the same platform. So I think one of the application that I said we've come up with, the second one, that was part of that study we published in IEEE Expo some time back. So from that work also, the evaluations that we did in that work were also formed part of this production. Yeah.
Right. I think people are satisfied. Thank you so much for your presentation, Isaac.
Thank you.
And that concludes our time together in this room. And so we can take our early tea break, and then you can re-strategize for your next sessions. Thank you so much.